So to prove that a sequence actually converges, at this point in the course, we need to know a priori what the limit of the sequence is, right? Because our definition of convergence actually requires us to specify what the value of L is. So we were talking last time about how the definition actually incorporates this limit L in it. So we have to know what the limit is before we can write a proof. So that's why in this first sort of structured problem that you're working on, the first step in that problem is to decide what that limit's going to be. So first of all, for these three sequences, so 2n over n plus 1, cosine of n pi, and n squared over n minus 1, which of these three did you select as the one that's going to be convergent? an. Okay, I agree with that. So how did you know that an was going to be the one that converges? What was your thought process, or what was your technique or tool that you used there?
For the an in particular, I learned early on that if it goes to infinity or looks over, then it's more likely to converge.
Okay.
So I kind of figured an would be it, but I just solved for the limit.
Okay, so yeah, one way to do it from Calc 2 is to kind of say, well, that the one which converges is going to be the one in which the numerator and the denominator go to infinity at sort of balanced rates, and so they can cancel one another out, or at least that the numerator doesn't go to infinity faster than the denominator. Allie?
The values of n are the exponents are equal, so you just take the ratio.
Yeah, so that's a little technique you can remember probably from pre-calculus that you first see this, that for a rational function, so both an and cn here are examples of sequences defined by rational expressions. Both the numerator and the denominator have the same degree as polynomials. It's linear on top, linear on bottom. As opposed to in cn, where we have a degree 2 on top and a degree 1 on the bottom. But when you first start talking about end behavior of functions in pre-calculus, these are the kinds of functions you can play around a lot with. And in the case of a rational function where the degrees are equal in the numerator and the denominator, how do you find the limit? I think Allie just told us, but can you say what you said one more time? You take the ratio of which coefficients? The coefficients of the highest powered term, in other words, the leading coefficients. So the reason that works, n plus 1, is what we're really doing there is we're really dividing the numerator and the denominator by that highest power. So since that highest power is 1 in both of these cases, we're really just dividing by n, upstairs and downstairs. n plus 1. I'm just going to divide by n. Divided by n. I'm going to be super archaic and use a division symbol here for a second. But yeah, that has the effect of leaving me in the numerator with just a 2. In the denominator, it leaves me with 1 plus 1 over n. And then I take the limit as n goes to infinity. But now the nice part is I've isolated my n's in this one little term here. Right? And so what happens to 1 over n as n goes to infinity? It approaches 0. If we know nothing else about infinity, we should know that as n goes to infinity, its reciprocal goes to 0. So I actually don't need to write the limit anymore. It comes out to 2 over 1 plus 0, which is exactly that ratio of the leading coefficients that Allie was telling us about. Right. So because this was a rational function, we can just do this little divide by the highest power trick, and that will help us to manage the rates at which the numerator and denominator are going to infinity, isolate the limiting behavior to just this one term, and give us our limit of 2. What's another way possibly to evaluate this limit from calculus? Yeah, L'Hopital's rule is another possible way, in which we would have taken the derivative of the numerator and the derivative of the denominator. We know we can do that because this has the indeterminate form, this limit has the indeterminate form, infinity over infinity, as n goes to infinity, right? And so we could, L'Hopital's rule is indicated in a situation like this. It would have given us the same answer. So the first step was we needed to know what the candidate limit actually is for this sequence. And now that we know what that limit is, let's go into our second part of this proof and replace that limit with the value 2. So now our job is to look at the definition of convergence, which now that we know that 2 is supposed to be our limit, let me write the definition of convergence up here at the top. For all epsilons greater than 0, there exists a capital N, which is a natural number, such that for all little n's that are bigger than or equal to capital N, we have that the absolute value of Sn minus L is less than epsilon. Right? So one of the things about this definition is it's complex. It's got a lot of things going on. It has 4 different clauses, right? It has the universal clause at the beginning, an existential that follows it, another universal that follows that, and then there's an inequality that needs to be satisfied. So there's a lot of moving parts. What turns out happening when you write a proof of a sequence converging is you tend to start with the part of this definition that kind of gives us something to work with algebraically, which is the inequality that's at the end. And what we want to do is take that inequality and turn it around so that in the beginning, where it looks like it's telling us something where epsilon is kind of the featured player here, what we really want in order to appease our definition is we want to know how to produce a capital N such that for all n greater than or equal to n, this inequality is satisfied. So we need to turn this around to somehow make n the star of the show, make n the subject of this inequality. So now we have an inequality to solve. But if we picked the right capital L for our limit, we should be able to do this. So how did you go from here? What did you do to begin the process of solving this inequality? So we'll start by replacing Sn by its definition, which here is 2n over n plus 1. And then we have minus 2. And then that absolute value is supposed to be less than epsilon. Okay. So now we have n's in our inequality that we can try to rearrange. Then what? Okay, so because we have an absolute value, there is a chance that the left-hand side of this expression could evaluate to just this. Right? It could evaluate to just the 2n over n plus 1 minus 2. Or there's a chance that if that quantity inside the absolute value is negative, that the sign would actually flip around. Right? That the absolute value of a quantity could be the quantity itself, or it could be the opposite of that quantity. So it could be that this evaluates to minus. Right? One or the other of those things is going to be true. And it might depend, as Eva's saying, it might depend on the value of n. Well, let's explore that question for a minute so that we know whether we can just dispatch with the absolute value. Well, we want to be able to dispatch with the absolute value, but when we do so, we want to know whether it gives us the original or whether it gives us the opposite of the original. So that's one way that we could start, right? Let's try just doing the fraction arithmetic. This is not the path that my Math 095 students would choose, but it's probably a wise one. Let's do the fraction arithmetic using a common denominator of n plus 1. And then 2 times the quantity n plus 1 is what I would end up subtracting here, right? And so let's try and simplify that if we can. Upstairs, 2n minus 2n, and then I'm also going to get a minus 2. So in fact, this simplifies pretty nicely into minus 2 over n plus 1. If I did my algebra correctly, and if I didn't, my evening students are going to pillory me. But now looking at it this way, can we decide what to do with these absolute values? What should I do with the absolute values? I should take them away and also take away the minus on the 2. Why? Because this quantity, negative 2 over n plus 1, how do I know whether this quantity is positive or negative? Well, the numerator is negative, right? But the denominator, n plus 1, is always positive because n is, by construction, a natural number, right? So positive denominator, negative numerator, that means this quantity is definitely negative. And even if I then split the absolute value over the numerator and the denominator, which we can, using properties of absolute value, in the denominator, those absolute values would just disappear because n plus 1 is positive. And in the numerator, those absolute values would cancel out the negative sign that we had and give me just 2 over n plus 1. So now I have an inequality. Now that my absolute value is gone, this feels like a more tractable inequality to have to solve. For solving this inequality for n, what should I do next? Yeah, let's just multiply by n plus 1 on both sides. So that I'll get 2 is less than epsilon times n plus 1. By the way, since this is an inequality, I have to be really super careful. How do I know that this inequality sign remains the same? Because n plus 1 is positive, right? So I'm multiplying by a positive quantity, guaranteed to be a positive quantity on both sides. So I shouldn't change the sense of the inequality. Okay. And then my step after that would be to divide by epsilon. By the way, how come I can divide by epsilon? Because epsilon is positive, and in particular, that means it's not 0, right? So it's not 0, which means I can divide by it on both sides, and it's positive, so that means I don't have to flip the inequality once again. Now my parentheses are superfluous, and my last step in getting n by itself is just subtracting 1. And then actually the last thing I'm going to do is just flip this inequality around. N is greater than 2 over epsilon minus 1. Okay. So now we're at the stage where we find that the inequality that we want to satisfy in order to appease the definition of convergent sequence, that inequality is logically equivalent to the inequality which says that n is greater than 2 over epsilon minus 1. So what we take from that is as long as this is satisfied, that will be satisfied. And the other great thing about it is this is an open-ended criterion, meaning that all n's which are greater than this number will satisfy this inequality. And so this clause for all n greater than or equal to n is going to be automatically satisfied as soon as I choose, in fact, any number which is greater than 2 over epsilon minus 1 can be my capital N, because then any number which is greater than it will satisfy this inequality and therefore that inequality. So this is where all the hard work went in. The only issue that's left is that 2 over epsilon minus 1 is probably not a natural number. Right? Let's say epsilon is, square root of 2 or something like that, right? Because again, this should work for any value of epsilon. This is probably not a natural number, but that's okay because we just need to find a natural number that's greater than it. How do we know that such natural numbers exist? Archimedes, exactly. The Archimedes principle tells us that there is a natural number which is greater than 2 over epsilon minus 1. So now, all we need to do is choose that natural number. And not in a specific fashion, but just in a fashion that's given to us by Archimedes. So here's the big finish for this part, is we're going to choose our natural number. And we just need to choose it so that it's greater than 2 over epsilon minus 1. One way of doing that, and we talked a little bit about this when we proved the density theorem 4 weeks ago or so, one way of doing that is just by taking that number, that real number, 2 over epsilon minus 1, and just rounding it up, right? Finding the next largest integer than 2 over epsilon minus 1. There's a nifty notation for that you might want to use. I don't know if anyone's seen this before. Does that look familiar to anybody? There's a little notation called a ceiling function, and all it really means is round up to the next integer, okay, the next largest integer. So if we round up 2 over epsilon minus 1 to the next nearest integer, then that's going to give me a natural number. And that then is going to be the magic natural number that I produce that's going to be exactly the right thing for my proof, if that makes sense. These little brackets, again, are what's called the ceiling function. It just means round up this number. Round it up to the nearest integer. It's called a ceiling. There's also a floor function, which is to round down, as well as a brackets, which mean round in the way that we usually think of round to the nearest integer. But for this example, I want to choose to round up because I need n greater than 2 over epsilon minus 1 to always be satisfied. So now that we've done all of this scratch work, This is the funny thing about convergence proofs, is that all of the stuff that happened in step 1 and in step 2, that often doesn't show up in the actual proof. All that scratch work is stuff that you do off to the side as you're discovering, first of all, what my limit should be, and then secondly, how to choose my n. So all of our work went into demonstrating this existential clause in here, right? The definition of convergence is that there exists an n such that, et cetera, et cetera. So we have to argue as proof writers why such an n exists. And one of the most compelling ways to do that is to give us a formula. Show exactly how to construct this n for any given epsilon. Right? And our n depends on epsilon because depending on how close we need to get to our limit, we might need to go further or less far out in the sequence before we get that close to the number 2. We'll look at the picture for that in just a second. So now to actually write the proof. This structure is more or less constant across every proof that you write of a sequence converging. And it's constant because it mirrors exactly the pattern of the definition of convergence. One step at a time. There's 4 clauses, and so there's 4 steps to the proof. The first step in the proof is literally to choose, in the sense of really not choosing, so I use the word introduce here, introduce the reader to epsilon. Because the first step in the definition is that we're supposed to prove something which is true for all epsilon greater than 0, no matter how small. So again, we have no control over what epsilon is. So the first step is for us to make peace with that fact. Sort of agree that somebody else is giving us this epsilon. And so usually what we'll write is we'll write, let epsilon be greater than 0, and maybe even more explicitly write something like this. Let epsilon be greater than 0, be arbitrarily chosen. So someone else has chosen this for us. Okay, so now that's done, right? Now we need to show that there exists a capital N that meets certain criteria. So our next step is to show that that N exists. So what we'll do is we'll take this N that we just did all this work to discover, and then we'll just plunk it right down there, a big meatball right in the middle of the table. And we'll say, here's our capital N, isn't it beautiful? So we'll here say define N to be the greatest integer, the next greatest integer, to 2 over epsilon minus 1.
You actually have to like find that.
No. Well, find what is the question?
Like, well, you define n to be like if you round up to the next nearest like natural number. So do you actually want to pick the next nearest?
No, the ceiling function does that for us, right? Because the number you pick is going to depend on the value of epsilon. Smaller epsilons, in fact, according to our construction at least, a smaller epsilon is going to make 2 over epsilon bigger, and therefore it's going to make the n bigger, which makes sense, because if we need to get closer to the limit, we probably need to go further out in the sequence before we get that close, right? Smaller epsilons tend to lead to bigger n's. So now here it is. And if I'm a proof reader, if this proof appears in a textbook, I'm only reading the stuff that's on the right-hand side of this line. And so as I'm reading this proof, I look at this and I go, what? Where did this come from? Right? This is almost like a proof writing sleight of hand, in a way. We did all the work over here on the side to bring this one thing suddenly to the table, and now we need to demonstrate that that thing was the right thing. Right? Now we need to show that this was the right choice for us to make. So we define our capital N, and then we say, all right, now we need to satisfy this last clause here, which is a universal clause again. It says that for all little n's that are bigger than or equal to this capital N, we need to substantiate why this inequality is true. So then the next step is to choose an n which is bigger than or equal to capital N. And again, because that's a universal statement, we have no choice over it. So we make peace and say, let n greater than or equal to this n be arbitrarily chosen. Someone else chooses a little n for us. Now we just have to, with all the information on the table, we have to prove that this inequality is necessarily satisfied for r Sn and for r L and for r epsilon. Right? So we'll say then, and we'll write absolute value of Sn minus L. And as is the case, anytime we're proving an inequality, we're going to work this inequality from the left side to the right by always replacing it with things that are definitely larger, right? Because all my inequalities are supposed to be going from smaller on the left to larger on the right. Well, we can start by doing as we did over here and replacing L with 2 and replacing Sn with 2n over n plus 1. 2n over n plus 1. So now you'll notice that some of the calculations we're doing are going to look very similar to the calculations we had to do to discover n in the first place. So it's not like it's totally opaque necessarily, because now we'll do the simplification that we did, where we combined the two fractions together. We took their absolute value and discovered that, hey, this is actually just 2 over n plus 1. Right? Absolute values went away because we realized the quantity inside the absolute value was negative, and so we flipped the sign. And now is when we use what we know about little n. And we don't know much about little n, but we do know that it's bigger than or equal to capital N. And that's all we need to know, because capital N, because it's the ceiling of 2 over epsilon minus 1, is greater than 2 over epsilon minus 1. Let me make that little comment up here. The reason we chose to round up is that that means that n is for sure greater than 2 over epsilon minus 1. And since that's true, we know that little n. So let me write this as a triple inequality here. Since little n is greater than or equal to big N, which is in turn greater than 2 over epsilon minus 1, that means in particular, since my little n resides in the denominator, if I replace my denominator with something smaller, it gives me a fraction whose value is larger. Denominator is a bizarro world. Remember, like anything which is larger in the denominator makes a smaller fraction. Smaller in the denominator makes a bigger fraction. So if I replace my little n with 2 over epsilon minus 1, and I leave everything else in my fraction the same, then since this is smaller than n, that makes my fraction greater than n, which is good, because that's what that's the comparison, the direction that we were trying to go in here. Right? But now you can see what happens from here. I've got some algebra that I can do down in the denominator. I can just kill those ones, get rid of the parentheses. I have 2 over epsilon. But what is 2 over epsilon? Epsilon. Well, how about that? So now taking a look at what we showed in our inequality from the left to the right, we've shown that absolute value of Sn minus L is, well, this is equal, less than, this is equal, epsilon, which is exactly what we were trying to prove. And this statement holds for all little n's that are greater than or equal to the capital N that we chose. And therefore, we've met all the requirements for this definition. And we have a very hard-fought little black box at the end of our proof.